Hello! In this lecture, we'll be exploring artificial neural networks. We'll start with a brief overview of their evolution from early efforts to the cutting-edge architectures we see today. This lecture will then cover the main concepts in neural network architectures and present practical examples of performing image classification, comparing implementations in both TensorFlow and PyTorch. Let's start with some background. Artificial neural networks, or ANNs, were originally inspired by our understanding of biological neural networks, though they are a simplified abstraction rather than a direct mimicry of brain function. While biological neurons communicate through complex electrochemical signals across synapses, artificial neurons process numerical values through mathematical functions. Although both biological and artificial networks process information through connected nodes, digital computers, including those that run artificial neural networks, operate using transistor-based logic gates, which function quite differently from biological neural systems. This image includes a screenshot from the TensorFlow playground. This is a neural network playground where you can tinker with a neural network in your browser and do such things as add neurons, add hidden layers, and test it on different data sets, in addition to fine-tuning some parameters. Now let's take a walk through the evolution of neural network models. We'll cover 7 key stages in this progression. In the early days of feed-forward networks, we begin in 1950s with the perceptron, which was designed by Frank Rosenblatt in 1958. This was the first artificial neural network capable of learning. In the 1960s, we saw the introduction of the multi-layer perceptron, or MLP, which added multiple layers of neurons to solve nonlinear problems. A crucial breakthrough came in 1986 with the backpropagation algorithm, which allowed for efficient training of multi-layered networks. This is an image from the original perceptron paper, and it is a link you can follow, which shows you the paper which is available if your institution has access. Moving into the 1980s, we see the rise of convolutional neural networks. A significant milestone was LENet5 in 1998, one of the first CNNs for image recognition. This link will take you to the published paper. And then the real revolution came with AlexNet in 2012, which dramatically improved image recognition capabilities. Key concepts in CNNs include convolutional filters, pooling layers, and shared weights, and we see these evolve at this stage. Parallel to CNNs, we have recurrent neural networks, designed to handle sequential data with internal memory. A major advancement came in 1997 with long short-term memory, or LSTM networks. These address the vanishing gradient problem that was present with RNNs. This link will bring you to the publication for LSTM. In 2014, we saw further improvements with the introduction of gated recurrent units, the GRU, The 20s and 2010s saw a deep learning revolution. Deep belief networks rekindled interest in deep learning. The introduction of the GPU computing enabled large-scale training of deep networks. This link shows an early paper of GPU computing, where we can see that with this capability, we are able to significantly improve the training time for our networks. And then we also saw more complex and deeper architectures like VGGNet, GoogleNet, and ResNet. In the 2010s, we entered the era of generative models. Generative adversarial networks were introduced in 2014, and these featured a generator and discriminator, which were competing to learn the data distribution. And I've included a link to that initial paper. Here we also saw the rise of variational autoencoders, or VAEs, as probabilistic generative models. And these models found applications in image generation, text synthesis, and data augmentation. In 2017 marked a significant shift with the Attention is All You Need paper introducing transformer networks. This link will actually download a PDF of that paper for you. And this was followed by BERT in 2018, which stands for Bidirectional Encoder Representations from Transformers. We've seen the rise in large language models like GPT-3, GPT-4, and PaLM. In our current era, we are seeing several exciting trends. These include multimodal models like CLIP and DALL-E integrating text and images, efficient architectures like DistilBERT, TinyML, graph neural networks for processing graph-like structures, and neuromorphic computing inspired by biological neural networks. For this link, I have chosen a paper that talks about opportunities for neuromorphic computing, algorithms, and applications. And I like that it also provides some coverage of implementations stemming from our traditional neural networks and how these can be evolved to support neuromorphic computing. Of course, there's also an increased focus on ethics, interpretability, and addressing biases in AI systems. Now that we've covered the historical progression, let's look at the basic architecture of a neural network. A typical neural network consists of three main parts: an input layer that receives raw data, one or more hidden layers that process information, and an output layer that produces the final result. The key components of the neural network are neurons, represented here as nodes, weights and biases, where the weights exist on each of the connections and we see a bias at each node, simplified in this diagram here. And then activation functions, represented with the alpha symbol. The processing in a neural network involves several steps. We start with forward propagation. Input data is fed into the input layer. Then a weighted sum is calculated, some bias is added, and an activation function is applied. This is followed by output generation, and then some loss function calculation, followed by backpropagation, where gradients are calculated and weights and biases are updated. This process is iterated over multiple epochs. Training a neural network typically involves supervised learning with labeled data, optimization algorithms like gradient descent, and hyperparameter tuning. Let's now walk through an example implementation using image classification. As we go through these examples, we're going to look at the code structure and the architecture of the neural networks implemented at a higher level, as this video is not intended to be a comprehensive how-to in deep learning for PyTorch or TensorFlow, but rather give you some code to get started with either or both of these popular Python libraries for deep learning. And if you hear some terms that you don't understand, that's something to research and look into, but don't worry about it. For this purpose, if you have experience training models, you'll be familiar with some of these terms. If you're very new to this, think of these code examples as an opportunity to take a top-down approach to start your learning journey in deep learning by simply copying the code and installing the libraries that you need and running the code. Here I've provided some example code implementing image classification using the MNIST dataset, which is a common benchmark in machine learning. And I've provided implementations in both PyTorch and TensorFlow. Again, in the description for this video, you will find a link to this web page that we're looking at. And from there, you can look at the PyTorch code, copy it, and then you can run that code on your machine, or if you would like, run it in a collaborative environment. The TensorFlow code, again, you can copy and run this code. And both of these implementations are solving the same problem. So we can compare the implementations. I'll scroll down to the start for the PyTorch code. So we start by setting up some parameters, an input size of 784, which represents 28 by 28 pixels in each of the images in the MNIST dataset, a hidden size, 256, the number of classes, 10, which is the target number of classes in the target output, so this is a multi-class classification problem. The number of epochs that we want to run, in this case set to 20. We have a batch size of 100 and a learning rate of 0.001, and these are parameters that you can fine-tune to improve the performance if needed. Here we're going to configure our PyTorch device. So we're going to use CUDA if it is available, meaning if you are running in an environment where a GPU is available to you. For example, if you are running this on your own hardware where you have GPU available, then you probably know what you're doing there. Or you might run it in Google Colab, which is an environment where you can select a GPU. And if you're not running this on hardware that has a GPU available, it's going to set the device to CPU. So we start by loading and preparing the data. This calls our load MNIST data function. If we scroll up and see the function definition, this is using a function called fetch OpenML. The MNIST dataset is a publicly available dataset, and we can go take a look and see what that looks like. This documentation is actually on the TensorFlow site describing the dataset, but within the dataset we have a number of images, and these images are of the digits 0 through 9, so handwritten digits 0 through 9. And we want to train a model to look at an image and correctly classify which digit 0 through 9 the image represents. So we can load that data set. We do need to do a little pre-processing. So loading the data set, we load it as a data frame with as frame set to false. And we're loading the data into features, which we'll store in our X variable by convention, and then the target, which is Y. So the target being the actual digit, and then the features being the image itself that we use to train the model with. Complete our pre-processing. Call the train test split method to split the data into a training set and a testing set, splitting both the input features and the labels, or the target variable Y. And here we need to convert them to PyTorch tensors. So this is some PyTorch specific code snippet to convert each of our data sets to a PyTorch tensor and then return them. So if we go back to our main function, we've loaded and prepared the data. So we have our training and testing sets for the features and the targets. And then we create data loaders for the training and testing data sets. We initialize our model. In this case, we're using a feed-forward network. And our function feed-forward-net, if we scroll up here, is going to describe our model. And we have this described with an input layer, some hidden layers, and an output layer. And we want to compare this to our TensorFlow implementation, which we've done a little bit differently for illustrative purposes. So this is setting up the layers. So when we set up our network, we are setting up the layers, and then we're setting up a method that defines how to forward process through the network. So how to feed forward through the network following the layers that we've established in the initialization of this feed forward net class that we've implemented here. Go back to the main method. So we've loaded our data, created some PyTorch specific data loaders, initialized our model using our feed forward net class that we created. Next, we're going to set up something to record the loss and perform optimization on our model. And here we're using an atom optimizer. And you can look at the PyTorch documentations to see what other optimizers and loss functions are available to you. Finally, we train the model. So we call a train model function, sending it all of the items that we have instantiated and set up. And then we evaluate the accuracy of the model, and we print out the accuracy. And in this case, we are going to plot the training loss so we can see what that looks like over time to see if we have a good model that converges well. The next code example is in TensorFlow. And in this case, I've written a script that just steps through step by step and follows closely along with the tutorial that's in the TensorFlow documentation. So we load our data as training and testing sets, where we have our input images being our features, and then Y being our output labels. And we're using TensorFlow with Keras in this example. We perform some normalization to set the pixel values in a range of 0 to 1 to improve our learning rates. We continue pre-processing by flattening our images to one-dimensional vectors to make them work for a neural network input layer. We're also going to one-hot encode the target labels, set up a simple sequential model for multi-class classification. Here we have a single hidden layer with 128 neurons with ReLU, R-E-L-U activation, and an output layer of 10 neurons for our 10 digits using softmax activation. And we'll compare this to the PyTorch model architecture. And then we compile the model using a categorical cross-entropy loss function and a stochastic gradient descent optimizer. Finally, we train the model and then evaluate the model by getting the loss and accuracy. And here we're just going to print those values. So what we want to do now is compare our TensorFlow implementation with our PyTorch implementation. So again, this code is provided for you to run and play with on your own. You can copy and paste it into your preferred environment, and it should run, provided you have the proper Python libraries installed. So let's compare the network architectures that we created. We'll start there. The PyTorch network architecture had an input layer of 784 neurons, flattened 28 by 28 images, 2 hidden layers with ReLU activation, 256 neurons each, and an output layer with softmax activation for 10 classes. Now this we configured when we set up the PyTorch architecture, when we established that model. In the TensorFlow network architecture, we created an input layer, again 784 neurons, and flattened 28 by 28 images. And here we have one hidden layer with ReLU activation, 128 neurons, and an output layer with softmax activation, 10 classes. So let's highlight some key differences between these implementations. The PyTorch version has 2 hidden layers of 256 neurons each, while the TensorFlow version has 1 hidden layer of 128 neurons. So this affects the model's capacity and performance. PyTorch uses an object-oriented approach with a neural network model, or NN.model, while TensorFlow is using a sequential API. In PyTorch, we have an explicit training loop, giving more control, while TensorFlow uses the built-in model.fit method. In the PyTorch code, we required manual device management for GPU usage, while TensorFlow is handling this automatically. In general, PyTorch might be easier to debug due to its Python native feel, while TensorFlow offers TensorBoard for visualization. Notably, there are some structural differences between the two implementations, which we mentioned, and this difference is meaningful in that it affects the model's capacity and performance. So I wanted to call out specifically that the PyTorch implementation has more parameters and therefore greater capacity to learn complex patterns. However, the TensorFlow implementation is simpler and may train faster. So that is a trade-off to consider when you are setting up a neural network implementation. And I've included a table here specifying the key differences in these implementations that we just talked about. So the definition of the model, the training loop, memory management, and debugging. Let's briefly touch on some key concepts that are covered by these implementation examples. The first one being multi-class classification. Our MNIST task classifies images into digits 0 through 9, so this is multi-class classification, and this is a problem where the model must classify input into one of several classes. So in this case, we have the digits 0 to 9, which is several classes in the output layer, using softmax activation to produce probabilities for each of these classes. So we'll have a probability in the end that each of the images matches one of the digits 0 through 9, given that those are our 10 classes. The activation functions that we used are ReLU in hidden layers and softmax in the output layer. So ReLU stands for rectified linear unit. This converts negative values to 0, allowing for better gradient flow during the training process. And then softmax, we talked about, converts raw outputs to probabilities that sum to 1, which is ideal for classification tasks. So if we have in our multi-classes, each output is a percentage and the percentages sum to 1, we can simply choose the higher percentage if there's a significant difference and state that that is the correct value for that image. Of course, depending on our application, we may need to have a certain percentage before we call something correct. We also have activation functions. Oh, I'm sorry, we just covered that. We have our optimizers, that we used. We used the Atom optimizer in the PyTorch implementation. This is an adaptive optimizer that combines things like RMS, prompt, and momentum. This generally provides faster convergence and better performance than SGD, especially for deep networks, but it does use more memory. And you'll note that in the TensorFlow implementation, we used SGD, which is a basic gradient descent with a fixed learning rate. This is simpler and uses less memory, but may require more tuning to achieve the optimal performance. But it's good for understanding the basic optimization process. The difference in optimizers may impact training speed and final model performance, with Atom typically converging faster, but SGV providing better generalization in some cases. So meaning while the training time may be decreased with Atom as it's converging faster, it may not generalize well to new data after being trained on a particular set of data. And we want models, in many cases, to generalize. The loss function categorical cross entropy measures the difference between the predicted probabilities and the actual classes, so the labels from our input data. And this is an optimal loss function to measure for multi-class classification tasks like MNIST. Looking at the expected performance metrics for a model like this, we typically expect training accuracy to be 98 to 99% after 10 epochs. So for this particular example, we do expect to have very high accuracy in our training. We expect the validation accuracy to be 97 to 98%. We expect the training time to be about 2 to 3 minutes on a CPU and 30 seconds on a GPU. So this is a nice example to get started with if you don't want to spend a lot of time training a model. And of course, the memory usage is low at approximately 500 megabytes of RAM. When tuning this model, there are some key hyperparameters to consider. And the hyperparameters are simply things that you can modify when you're training the model to try to improve that model's accuracy. For example, the learning rate can be modified where higher values train faster but may be unstable. So you're provided a range here of 0.0001 to 0.01. The batch size can also be tuned. If we look at a range of anywhere between 32 and 256, larger batches are going to use more memory, but they're going to train faster. So depending on how much memory you have, you might want to change that hyperparameter. The size of the hidden layers. We discussed this when we were comparing our two implementations. Larger networks can learn more complex patterns. So the hidden layer size, you might try playing with different sizes from 64 to 512. And then, of course, the number of epochs. More epochs will allow better convergence, but they might risk overfitting. And overfitting being where the model has trained on a specific input data set and it has overfit that data so that it does not generalize well to any different data sets that it encounters, so unseen data. So you might try adjusting the number of epochs in the suggested range of 10 to 50. There are also regularization techniques that you can try. Dropout and L2 regularization. Dropout randomly deactivates neurons during training. And you can use this when your model is overfitting. Setting this to a range between 0.2 and 0.5, higher rates mean more regularization but slower learning. And in L2 regularization, this penalizes large weights. We use this for general purpose regularization. Smaller values mean less regularization with a range 0.01 to 0.0001. In looking at how well your model performed, you might want to employ different visualization techniques. Looking at training curves, plotting the loss in accuracy versus the number of epochs to identify if your model is overfitting or underfitting. Plotting a conversion matrix, which allows you to visualize which digits are being commonly misclassified. And layer activations, where you can inspect what patterns each layer is learning. Remember, there's a trade-off between model complexity and performance. A simpler model trains faster and is less likely to overfit, but it may underfit complex patterns, meaning it may have very poor prediction rates on complex patterns. While a more complex model can learn intricate patterns, but is prone to overfitting and requires more resources. So along those lines, the model complexity trade-offs from this example, a simple model with one hidden layer and 128 neurons is going to, as the pros, have fast training, less memory, use less memory, and is less likely to overfit. But the cons are it may underfit on complex patterns. And then our complex model with 3 or more hidden layers and 256 or more neurons, this can learn more complex patterns, but has slower training, uses more memory, and is prone to overfitting. So for this, a simple MNIST data set, a simple model is often sufficient. And you might consider complex models only if the simple ones underperform. So start with a simple model, and if it's underperforming, and you have tried to optimize it using hyperparameter tuning, and you might consider increasing to a more complex model if it is still overperforming. We've covered a lot of ground in this lecture, from the early days of neural networks to cutting-edge architectures. We've seen how these models have evolved to tackle increasingly complex tasks, and we've even implemented a basic image classification model. As we look to the future, it's clear that neural networks will continue to play a crucial role in advancing artificial intelligence and solving real-world problems.